Hi, my name is Kimball Germain, and this talk is about how heap fragments can improve must-alias analysis for higher-order programs. Let's start by considering procedure inlining, a fundamental program transformation used by optimizing compilers, and a client of must-alias analysis. Suppose that we want to inline the function call to f in the program shown. Well, our first task is to determine what flows to f. The value bound to f is produced by a call to process, and so it's not apparent what function we should inline. To determine which values to which f can be bound, we can use a control flow analysis. Suppose that a control flow analysis shows that only closures over the highlighted lambda flow to f. Next, we need to ensure that any free variables in the closure are in scope at the call. In this case, we have a free variable y, bound by an enclosing lambda. And this enclosing lambda also encloses the call to f. Syntactically then, it's sensible to inline this lambda at the call to f. However, is this operation safe? Let's consider a more concrete example. This program first defines a function g. G checks whether its first parameter x is 0. If so, it calls its second parameter h and returns its value as the result. Otherwise, it returns a closure which captures the binding of its first parameter x. This program then calls g so that x is bound to 42 and h is bound to false. The check for whether x is 0 fails, so g returns a closure over the current binding of x, which is to 42. The program then calls g again, this time binding x to 0 and binding h to the just returned closure. This time, the check for whether x is 0 succeeds, and g proceeds to call h. When we call h and invoke this closure, the result will be 42, and that will be the result of the program. However, a control flow analysis will show that at this point in the program, only closures over this particular lambda flow to h. This lambda has a free variable x, which is in scope. As before, it seems like we should be able to inline. However, by inlining the function and reducing, it becomes clear that we've changed the meaning of the program, for this x is returned only when guarded by a check for whether x is 0. Thus, our active inlining has changed the result of the program from 42 to 0, and is thus unsafe. The issue that we failed to consider is that at the call to h, there are multiple bindings of x reachable. Because these reachable bindings to x are distinct, it was unsafe for us to replace a reference to one by a reference to the other. However, if these two bindings alias one another, it is safe for us to change a reference to one to a reference to another. This is why must-alias analysis is critical for an otherwise mundane optimization, procedure inlining in a higher order language. Going back to our initial example, we can see the same pattern of binding occurring. Both the call to f and the lambda, which captures y binding, lie within y's scope. However, as we have just seen, this condition alone does not suffice to prove the safety of the inlining operation. The solution to the aliasing problem that we build on is abstract counting. The abstract counting technique maintains a count of the number of concrete entities that a given abstract entity represents. When embedded in an operational framework, abstract counting is manifest as an enriched heap, which maps addresses not only to denotable values d, but also to account of the number of concrete entities represented by that abstract allocation. Abstract counting is capable of maintaining whether each abstract allocation corresponds to 0, 1, or multiple concrete allocations, represented here by 0, 1, and infinity, respectively. On the right is a heap enriched with abstract counting. Alpha naught maps not only to a set of closure values, but also to an abstract count of 1, indicating that this abstract allocation corresponds to one specific concrete allocation. Alpha 1 maps to a natural number n and also has an abstract count of 1, indicating that this abstract number n, although its value is unknown, refers to one specific concrete number. Alpha 2 also maps to an abstract number n, but its abstract count is infinity, indicating that its unknown value represents multiple concrete values. The operational framework in which abstract counting has been historically embedded has made it unable to maintain precision in the face of certain patterns of recursion. To see why, let's reconsider the initial example program, but this time in recursive context. First, we will assume that this lambda is given a recursive binding. Next, we will assume that it calls itself recursively. In the body of the let, we have added a recursive call to loop, followed by a call to f, such that the results of each call are combined using the function combine. Let's walk through an analysis of this program to see this weakness firsthand. On the left, we have the program, where the highlighted portion of the program is the part of the program which has control within the analyzer. On the right, we have a model of the heap. In this operational framework, evaluation of each part of the program is performed with respect to the entire heap. We will walk through a zero Cfa analysis of this program, meaning that the variables in the program and the addresses in the heap are in one-to-one correspondence. Although zero Cfa, a context-insensitive analysis, is among the least precise of control flow analyses, the weakness we observe is present in context-sensitive control flow analyses as well. The first step to evaluate this letrec is to evaluate the right-hand side of the binding. This creates a dummy entry in the heap with an abstract count of 1. This expression is a lambda, which is a simple expression, and evaluates immediately. We then proceed to the body of the letrec. Now, the binding to loop has been resolved, and we can perform the call. As we perform this call and enter the function bound to loop, we allocate two new bindings in the heap, one for x and one for y. Because each of these bindings is new, they have an abstract count of 1. We will skip over the evaluation of the right-hand side of the let and instead proceed to the inner call to loop within the body. Notice before we make the call, though, that the binding for x in the heap has been removed. This is because this framework uses the technique of abstract garbage collection to remove bindings that are not reachable from evaluation from the heap. This increases precision. The binding for y has not been removed, however, because it is reachable from the function bound to f, and f is reachable from the continuation of the recursive call to loop. As we enter the call to loop, two new bindings of x and y are made. Because there was not a previous binding of x in the heap, the binding for x has an abstract count of 1. However, because the binding of y existed in the heap already, the new and the old binding are merged, and the abstract count becomes infinity, indicating that it represents multiple concrete bindings. What we have seen is that when we have a recursive call that is not in tail position, where some of the bindings of the function are reachable from the continuation of the call, that we completely lose precision with respect to those bindings. This diagram depicts the conventional operational model, an open expression on the left whose free variables reference bindings resolved in the entire heap on the right. We address the weakness of this operational model as it stems from the shared use of the entire heap by splitting the heap into fragments as evaluation proceeds, one fragment for each stack frame. This separation into fragments allows multiple bindings to the same abstract address on the stack, a hallmark of many recursive patterns, to remain isolated and allows abstract counting to maintain precision. To see how heap fragments fortify abstract counting, let's perform the same analysis as before, but this time with heap fragments. In this analysis, each expression and frame maintains its own heap fragment. The expression with control is the expression on the top of the stack. As before, we evaluate the right-hand side of the loop binding, a lambda, and proceed to the body of the letrec. In making this call, we introduce bindings for x and y into the heap fragment, each with an abstract count of 1. Up to this point, the analyses exhibit the same precision. Again, as before, we skip the right-hand side of the let and proceed directly to the recursive call to loop. Notice that the heap reference to y present in the previous analysis remains in the heap fragment for the call's continuation frame, but does not appear in the heap fragment of the call itself. Thus, when the call is made, both the bindings of x and y are fresh to the heap and enjoy an abstract count of 1. The analysis has encountered this precise configuration of expression and heap before, just 2 slides ago, which the analyzer detects to tie the recursive knot. In the end, we have a more precise account of aliasing, which allows us to justify inlining in the recursive context, and the analyzer has explored a smaller state space to achieve it. To maintain the stack correspondence necessary to use heap fragments, the analysis requires a push-down model of control flow, which is furnished by a so-called push-down precise control flow analysis. This shifts the operational model from one which models heap snapshots to one that models heap change summaries. This shift has a non-trivial effect on the abstract counting machinery, which we discuss in the paper. The use of heap fragments also allows us to instantiate a more general form of binding alias analysis known as binding invariants, which we recount in the paper. Because a heap fragment need only close an individual stack frame or expression, abstract garbage collection determines more bindings to be irrelevant, leading to significantly smaller heaps within configurations. This tendency should result in analyses which explore smaller state spaces and have more precision. Our empirical evaluation offers evidence that this is indeed the case, with many instances showing the effect dramatically. Thank you.
Welcome, and thanks for tuning into my talk on graphs, declarative graph analytics. My name is Farzin Hushman, and this is a joint work with Mohsen Vassani and Keval. If you look at the world around you, you'll see that graph applications are everywhere. They are a backbone of important services in different domains, such as social networks, search engines, recommendation systems, and even computational biology. Achieving high performance is crucial to these applications. Therefore, they require scalable implementations to process graphs with billions of nodes and edges. There has been a growing number of high-performance graph processing frameworks across shared memory and distributed platforms, such as Lygra and Gemini and Greenmore. However, existing frameworks provide programming models that are low-level and different from each other, making it challenging for the end user to implement and optimize programs. On top of that, there isn't any sort of guarantee about the correctness of programs. Also, existing declarative languages such as Fragments and Elixir require users to write the kernel functions. As an example, BFS is expressed differently in Lygra, GridGraph, and Gemini, which require knowledge about each framework. The goal is to have high-level abstraction for graph analytics, which helps us to write correct and optimized programs. As a solution, I present Graphs. Graphs is a high-level declarative language for graph analytics. It features semantics-preserving transformation rules that optimize the program. We have identified three core primitives in graph analytics called iteration, map, and reduce. Graphs is backed with formal definitions of iterative models and their correctness and termination conditions. Having the vision of using automated reasoning to build rigorous systems in mind, Graphs synthesizes kernel functions for iterative models and generates code for 5 high-performance graph frameworks. The workflow of Graphs is as follows. Given the specification of a program, Fusion rule transforms the specification to the three primitives of iteration, map, and reduce. Then the fused form is passed to the synthesis engine to generate correct and construction kernel functions. Finally, given the kernel functions, the low-level implementations for each framework are generated. Graph supports different classes of graph analytics. First are problems that iteratively calculate values for each vertex, such as Google's PageRank or connected components. Second are traversal and path exploration problems, such as BFS and single source shortest path. And finally, social network analytics use cases, such as calculating radius of a social network or finding trust circle of a user. Generally, these are the algorithms that reduce values over paths, hence we call them path-based graph analytics. Let's go over examples written using Graph's declarative language. Take a look at the specification of single source shortest path routed at S. The value of vertex V is defined as the minimum weight of all the paths that start from S and ends in V. Another example is the radius. The radius of a graph is defined as the minimum eccentricity over all the vertices, where eccentricity is the maximum distance of a vertex to others. And finally, an interesting social network analytics, least trust. Least trust measures the least amount of trust from a user to a neighborhood in a social network. Given the definition of single source shortest path and widest path, L trust of S calculates the widest path to each vertex within the radius of S. Capacity of paths can represent the trust value from the source to destination. Therefore, L trust calculates and returns the narrowest of those paths. I'd like to emphasize on the fact that programs written in Graph's language use mathematical notations, therefore they are concise and as short as possible. Now let's take a closer look at the specification language. The declarative language of graphs precisely captures path-based graph analytics. Consider the radius example that we just saw earlier. Radius is calculated by getting the minimum eccentricity over a set of sampled vertices. Therefore, in the first step, we need to calculate the shortest path length to all the vertices. This is done by applying minimum reduction function to the result of length path function. We have modeled known path functions such as length, weight, and capacity. Also, the reduction functions are from the known reduction operators. Reduction of these sorts are called path-based reduction and have the general form of applying reduction function R to the result of a path function for a set of paths. We will later see that path-based reductions can be calculated using iterative models. The path-based reduction can also be represented with an islet term that binds the variable x to the result of the path-based reduction at each vertex. Mapping over vertex values can be achieved by combining multiple path-based reductions with binary operators. The map operation in this example is simply the identity function. Next, we need to calculate the eccentricity for all the vertices by applying the maximum reduction function to the shortest path computation. In graphs, reduction function can be applied to the result of a path-based computation, and it's called a vertex-based reduction. Finally, the minimum of the eccentricities over a set of sample sources are calculated. In graphs, a vertex-based reduction can be written as a triplet construct, which separates terms for path-based reduction, mapping over vertices, and vertex-based reduction. Later, we see that triplet form is easily implementable using the primitives of graph analytics called iteration, map, and reduce. As for the semantics of graphs input language, here I present one of the rules. You can find the complete list of the rules in the paper. The rule SPRED defines the denotational semantics of a path-based reduction. At each vertex V, this rule applies the path function to each path to V, then applies the reduction function R to the resulting values. The semantics of graphs are compositional, and we have formally proved that if two terms are semantically equivalent, replacing one with other preserves the semantics. This lemma is important since compositionality of semantics allows fusion rules to optimize the specification. The next step is the fusion. Executing multiple rounds of path-based reductions sequentially result in redundant operations on edges and vertices. Consider two path-based reductions, the red one and the blue one. Naively, they can execute in sequence. However, same operations would take only one round when fused together. Therefore, the fused version eliminates redundant operations. With that said, fusion is a set of rules that transform the specification to a single triplet by combining similar operations. We have formally proved that fusion transformation is semantics preserving. We have identified three fundamental primitives of graph analytics called iteration, map, and reduce. And fusion converts the specification to these primitives. Generally, there are three types of transformation. First is fusion of the path-based reductions. Second, fusion of mapping operations over the results of path-based reductions. And finally, fusion of the vertex-based reductions. Consider the radius calculation sampled over two sources, S1 and S2. First, the vertex-based reductions starting from S1 and S2 are transformed to triplets separately. In the next step, the two triplets are fused together by creating a pair for path-based reductions and vertex-based reductions. In this example, there is no mapping, so the map expression simply returns the path-based reduction. Then the pair of path-based reductions are transformed to a single path-based reduction that operates on a pair of values with the following path function f and reduction function r. Here, I'm going to take a second to show the fusion rule that is applied in this step. Rule FM pair transforms all pairs of path-based reductions to a single path-based reduction, such that the path function applies a pair of path functions to a path, and the reduction function operates on pairs of values. Finally, the pair of vertex-based reductions are transformed to a single vertex-based reduction R prime that operates on pairs of values. We saw graphs specification language and how fusion transforms it into iteration, map, and reduce. Mapping and reduction over vertices can be implemented by traversal over the vertices. Here we review iterative models. The iterative models are algorithms that calculate path-based reductions. In graphs, we have formally modeled 9 variants of iterative models with different directions, reduction functions, and synchrony types. All these models are parametric in terms of graph analytics kernel functions. In graphs, we have defined a high-level language for the kernels. Consider SSSP example rooted at S. Initialization initializes vertices by setting the value of source vertex to 0 and the rest of the vertices to undefined. The propagation propagates the new weight by adding weight of edge E to the current value. And finally, the reduction function aggregates values and returns the minimum weight. Let's consider the pool model with idempotent reduction. The value of the vertex V at iteration k is represented with sk of V. In the beginning, all the values are undefined or bought. The calculation starts by initializing vertices with the initialization function. Now let's consider vertex V in the kth iteration. The active vertex V starts pulling the propagated values from all the incoming neighbors. The value of the vertex V in the next iteration is then calculated by applying reduction function R over the pooled values and the current value of V. Finally, if the value of v changes, the outgoing neighbors are set to be active for the next iteration. The iterations continue until the value of all the vertices stay unchanged. The correctness of the iterative models depend on a set of correctness conditions for each kernel. Here I only highlight a subset of conditions. The conditions for the reduction function are straightforward. R must have the following properties: identity, commutativity, associativity, and idempotency similar to the iterative model. Given a path-based reduction that starts from the source S, the correctness condition for initialization requires the value of the source vertex S be equal to the result of applying the path function to the initial path within 0, and the rest of the vertices to be undefined. The condition aggregate propagation is the crux of conditions for propagation function. This condition states that reducing the path values of P1 and P2, the local propagation of the result along the edge E should be the same as reduction of the global calculation of the path values for two extended paths P1E and P2E. Therefore, the condition checks for the following equality for the propagation function. Using the correctness conditions, we have formally proved the correctness and termination of the 9 variants of iterative models. For example, the correctness of the synchronous full idempotent model states that if all the correctness conditions for the kernel functions are satisfied, at the end of kth iteration, the value that the model calculates complies with the specification. We have reviewed the correctness conditions for the kernel functions. Now let's see how they are used to synthesize the kernels. To synthesize kernel functions of a path-based reduction, Graphs uses syntax-guided enumeration on the grammar of the kernel functions to generate candidate programs. Then the validity of each candidate is checked against the correctness conditions using the Z3 SMT solver. We have modeled the graph's path functions and relations in the combination of the quantified uninterpreted functions and least theories. The output of the synthesis engine is then correct by construction kernel functions. Now I'm going to wrap up the presentation with a highlight of the experimental results. All the experiments are done on a 4-node cluster. Graphs can generate code for LiveGraph, GridGraph, Gemini, PowerGraph, and Graph at runtimes. This table here shows the list of the use cases that graphs successfully synthesize. We observe that graphs can generate each use case efficiently in less than 2 minutes. Also, comparing lines of code written for each program in different frameworks versus graph specification language shows that programs written in graphs are significantly smaller. Our first set of experiments are to show that fusion leads to fewer number of operations. To do that, we have collected the ratio of the processed edges in the generated programs over unfused implementations for 3 programs. The results indicate fusion reduces number of edge operations by up to 75%. Also, the reduction in number of edge operations translates to up to 4 times speedup across different frameworks. Finally, after studying the scalability of the fused programs in the LiveGraph framework with increasing number of cores, we observed that the speedup with respect to the handwritten programs remained steady, and the fused programs scale similar to the handwritten ones. In the conclusion, fusion preserves the parallelism of the specification and never rely on major synchronization bottlenecks such as locks. Wrapping things up, I presented graphs, a high-level declarative language for graph analytics. It features semantics preserving optimization rules. We have modeled iterative reduction models and their correctness conditions. Using the correctness conditions, graphs synthesizes kernel functions, and finally our results on fused programs showed up to 4 times the speedup compared to the handwritten implementations. Thank you all for watching.
Hi, I'm Yasu Watanabe, here to talk about my joint work on certified program synthesis with Kiran Gopinathan, George Pirlea, Nadia Polikarpova, and Ilya Sergey. Imagine you're a developer and you need to implement a specification of a program that creates a copy of a linked list expressed in separation logic. And the precondition is a reference pointing to the head of a singly linked list, whose presence is expressed with this inductive predicate. In the postcondition, eventually we want the original list plus a copy with identical elements and an updated reference pointing to the head of the new copy. And this connective is called a separating conjunction, which says that the left spatial part is disjoint from the right. The linked list predicate is defined with two constructors, an empty case when x is a null pointer, and a non-empty case when x points to the value at the head of the list and x plus 1 points to the tail. At this point, any other developer would roll up their sleeves and start coding. But you know better than that. Instead, you feed the specification to Syslic, a program synthesizer that can automatically produce an implementation from a user specification. And voila, you get a list copying program. But just then, you're hit with a wave of uncertainty. Can I trust this result? The synthesizer was written by humans, so surely a bug could make it synthesize incorrect programs. Can we have a guarantee that programs synthesized by Syslic correctly implement their specifications? In this work, we discuss a way to produce this formal guarantee in the form of proof certificates for each synthesized program. The technique consists of generating these certificates using the deductive insight gained from synthesis. Let's return to this issue of trust. Our earlier misgivings arose because Syslic has a large trusted codebase, or TCB. Ideally, we'd like to offload the burden of trust to something with a more minimal TCB, like the Coq Proof Assistant. Coq proof certificates are widely treated as a correctness guarantee for important theorems and programs. Syslic's codebase is quite large, so it's impractical to verify its entirety in Coq. But luckily enough, Syslic's deductive approach to synthesis makes it suitable for post hoc certification, where we generate proof certificates for each synthesized program. To see how it could be done, let's understand how Syslic synthesizes programs from specifications. Syslic operates in the logical framework of synthetic separation logic, or SSL. An applied SSL rule transforms a synthesis goal into another one, while also emitting a residual program statement. Syslic synthesizes programs by enumerating the search space of SSL rules until the goal is reduced to a trivial entailment and a program is found as a byproduct. In theory, the sequence of SSL rules applied to synthesize the program should be all we need to build a valid Coq certificate. Interestingly, though, there's a fundamental gap between synthesis and verification proofs, which prevents a straightforward generation of these proof certificates. In verification, a program implementation is known ahead of time. This means we can use its structure to guide the proof, symbolically executing a proof step corresponding to each program statement. The precondition P is transformed as we go. Notice how postcondition Q stays untouched. Only at the very end does the fully symbolically executed precondition PM get unified with postcondition Q. In contrast, during synthesis, we can't rely on an existing program structure, since that's what we're trying to derive. Instead, each successful application of an inference rule incrementally transforms the specification until it becomes a trivial entailment. Here, both the pre- and postcondition are transformed. For this reason, when SSL rules transforming the postcondition appear earlier in the synthesis proof tree, their insight needs to be deferred to the end of the verification proof. So one big question is how to bridge these two different styles of reasoning. Another consideration is that multiple program verifiers embedded into Coq can do separation logic proofs like Hoare type theory, or HTT, verified software toolchain, or VST, and Iris, to just name a few. How do we uniformly support certificate generation for all of these verifiers? These two challenges form the basis for our work. To overcome the synthesis verification gap, we need a way to interpret synthesis proofs into verification ones. And to remain verifier agnostic, it must be an abstract framework that multiple target verifiers can instantiate. For these reasons, we present a design for an abstract proof evaluator that interprets a synthesis trace into a machine-checkable proof certificate. We then demonstrate the generality of the evaluator's design by instantiating this abstract evaluator for the three verifiers, HTT, VST, and Iris. And finally, we apply this technique to certify Syslic's synthesis of characteristic benchmark programs. Let's see how this abstract evaluator works. We can instantiate the evaluator for a target verifier by providing a custom proof step interpreter, which maps an SSL rule application in the synthesis proof tree to a corresponding step in the proof certificate. After synthesis, an instantiated evaluator traverses a proof tree encoding of the successful derivations and invokes the interpreter at each node to build the certificate. Now, I'll explain two strategies the evaluator uses to bridge the gap we observed earlier. First, we have deferred proof steps, the ability to delay the appearance of a proof step beyond when it's first interpreted. Intuitively, it behaves like a continuation in functional programming. Second, we have proof contexts, which let the interpreter store and later retrieve bookkeeping information throughout the traversal. The functional programming analog would be an accumulator. Using the instantiation for Hoare type theory, I'll now show how these features help our evaluator certify the list copying example. On the left is part of the synthesis proof tree, with the rest of the tree truncated at the bottom, and on the right is an HTT proof certificate. Some steps are easy to translate, like this read rule of SSL and its HTT counterpart. So, our proof step interpreter just needs to map the rule to HTT's bind read R lemma. Other rules aren't so easy. In the second branch of the proof tree, everything is in the right order until this close rule. Close unfolds a constructor of an inductive predicate applied in the post condition. In our example, this occurrence targets one of the two singly linked lists from the specification's post condition and unfolds the predicate's second constructor. If you recall, such rules that transform the post condition must appear at the end of the verification proof in the final unification step. This is where deferred steps come in. Instead of emitting the counterpart step immediately, our interpreter can choose to add a step-producing computation to a queue. The queue grows with items during traversal and gets released at the end of the proof. Like a continuation, this gives the interpreter some control over how proof steps get ordered. But if you look at the deferred step that gets computed from the close rule, you'll notice that the existential variables of the unfolded predicate constructor don't quite match up with what's actually needed in the HTT proof. This is because when this step was first enqueued, Syslic referred to the existentials by their default names. But a few nodes later, S prime is unified with another variable, S1, by this unify rule. Similarly, the other existentials also get their correct values later on. To keep track of these substitutions, we introduce an accumulator-style proof context, which each invocation of the interpreter can update. For our example, let's add the first substitution to the proof context at the unify rule and do the same for the other two. Now, the enqueued computation can access this substitution knowledge at the end of the proof if we parameterize it with a proof context argument and invoke it with the final proof context. This way, the emitted step will have the correctly substituted existential variable names. That was an overview of two features of our proof evaluator inspired by continuations and accumulators. To assess our design, we wanted to answer two questions: the efficiency of the certification in terms of proof size and checking time, and any synthesizer or verifier design choices that complicate automated certification. To determine efficiency, we evaluated this technique against a number of other programs that Syslic can synthesize. Proof sizes are relatively concise. Proof checking times are between 2 to 20 seconds for most of the HTT and Iris examples. VST proofs take longer because the generated scripts rely on a VST automation tactic whose generality incurs a performance cost. For our second question, we found two key challenges. One is the difference in difficulty implementing support for each target verifier. HTT was the simplest. Thanks to its shallow embedding of both SL propositions and object language, there was no need to distinguish program and proof level terms. VST is notable for targeting real, machine-executable C programs. Although VST provides advanced proof automation support, it surprisingly didn't always make things easy for us. Unlike HTT, VST uses a lot of custom notation to simplify the proof context, so in order to design additional proof automation tactics, we had to dig into the implementation details behind the nice notation. Naturally, this made the corresponding automation more fragile. We faced the most difficulty with Iris, whose standard human-guided proofs require lots of explicit goal management and hypothesis name tracking, to a degree that it's troublesome even with our proof context. So we extended Iris with new tactics to let us write proofs in Syslic's proof style that relies heavily on heap unification. Unfortunately, Iris's unification tactics are more fragile compared to VST's, so it needs to be done very carefully to keep the proofs tractable. Another challenge was recreating the steps performed during synthesis that aren't recoverable from the proof sketch. Pure non-spatial assertions aren't handled much by separation logic, so Syslic delegates their checking to external SMT solvers, which act as an oracle to determine whether an implication is valid or not. On the other hand, a proof assistant like Coq needs a constructive proof of the same facts more than just the yes or no answers that SMT solvers can provide. So to match the oracular insight of SMT solvers, we turn to certified solvers, or hammers as they're generally referred to as. Hammers are single-line commands that enable powerful proof automation capabilities. They usually work by communicating with an external automated theorem prover, or ATP, to find a solution using the lemmas available to it. For our purposes, we extracted and formatted pure entailments like this into lemmas, and then solved them with Coq Hammer, a certified solver library. Then, by adding the proved lemma as a hint, it can be used by Coq's automation tactics during the main proof of the program. As a stretch goal for HTT, we also certified some additional, more complex programs. For all of these, the main proofs went through, but sometimes the certified solvers needed manual assistance to solve the extracted auxiliary pure lemmas. In the future, it could be interesting to explore some middle ground between full automated and user-guided certification. To summarize, we sought to bridge the gap between synthesis and verification. We introduced an abstract proof evaluator framework with features inspired by continuations and accumulators. We then instantiated the evaluator for 3 verifiers and certified around 15 characteristic benchmarks with all 3, plus some extras with HTT. And with that, we have fully certified program synthesis. Thank you for listening.
Hey, this is Adam Chapala. At MIT, I teach a class on formal semantics and program proof using the Coq Proof Assistant. And this functional Perl is my chance to share with you an approach that we use in that class to get the interesting stuff more quickly. So there's actually quite a lot of coursework going on these days that builds on proof assistants to help students learn to reason about programs. Two of the best known materials are Programming Language Foundations and Concrete Semantics, which both start from students who don't have past experience with proof assistants. There are also other materials, including my own book, Certified Programming with Dependent Types, that are aimed at people who are maybe more interested in becoming experts on these tools and get into more advanced material. So let's think about the benefits of these different styles. On the left, we can start with students who have minimal background, just basic undergraduate stuff that we assume all of our graduate students come in with, and we can teach them how to use proof assistants, how to prove the correctness of programs. Whereas on the right, we get to more advanced topics that I at least believe are crucial for scaling to, say, correctness proof of real-world programs. How can we get some of the benefits of both sides here? In particular, if we think about what a typical software foundations course accomplishes, by the end of the first part on logical foundations, let's say students finally get how to think about induction, how to do their own induction proofs. And when they pass through the second part, programming language foundations, they can do manual proofs of such classic results as type safety and correctness of individual programs in simple imperative languages. Could we, within a single semester, ideally, push this further so that students can actually do automated proofs of shared memory concurrent programs that do interesting things with mutable memory? I will say yes. So the class that I offer tries to mix some of those advantages. We will only assume standard undergraduate background in programming and theory. We will still take every proof principle we introduce and justify it from first principles. But we will also work with full-featured object languages, that is, the languages that we study formally, that really let you write real-seeming programs. And we'll do a lot of proof automation to save students from having to spend their time on the less interesting parts of proofs. So how do we do that? How do we cut out the less fundamental parts of this kind of reasoning? So we all know, for instance, the beta reduction rule of operational semantics for lambda calculus, which depends on substituting a value for the body of a lambda binder. We worry if v were not a value but actually contained free variables of its own, then those could accidentally be captured during substitution if the same variables are bound inside the body E. And in some kinds of semantics, we actually do need to do substitutions that are not only on values. And then we get some pretty hairy requirements that have caused a lot of trouble for people doing mechanized proofs. Another related example, let's think about separation logic. One of the most famous ways of reasoning effectively about imperative programs. And here is the frame rule that was really at the heart of the original proposal for separation logic. Above the horizontal line, we see the premise, which says we've proved a precondition P and a postcondition Q for some command. And then we're allowed to conclude for free any larger specification where we take the same predicate R and we added onto both the precondition and the postcondition, describing the contents of some disjoint region of memory. This is a really nice, elegant way of thinking about why we can, for free, lift results into larger memories. Unfortunately, it comes along with this side condition. No variable occurring free in R is modified by C. So before we get to the fun part, we have to explain free variables of predicates and modified variables of commands. Is that essential? One last example before I get into the solution. Let's think about shared memory, multi-threaded programs. One thread is incrementing its local variable x and then writing the result into a shared pointer, and then thread 2 is doing a symmetrical thing. In model checking, we might explicitly explore the state space of this kind of program, considering every point where we have to choose which thread runs next. In one path, first thread runs doing its x increment, and then the second thread runs doing its write into the pointer. But in fact, those steps could have happened in the opposite order of that, and we wind up in the same state, independently of the order that we choose. And in fact, production scale model checkers need to notice and take advantage of commutativity properties like this one to do their jobs well. And to formalize the rule that lets us detect when two operations commute, we might, for instance, say a command that only touches local variables of its thread commutes with anything the other threads want to do. But now we need to be rigorous about global versus local variables, and we need to justify that reasoning principle. Okay, so what do these three examples have in common? Well, let me show you a demo. So I'm going to start with maybe a more conventional way of doing a calc embedding of a simple imperative language. And then I'll show you how we do it differently with the approach that I'm here to sell you, which is mixed embeddings. So by the way, this should make a decent amount of sense to a general functional programming audience. Hopefully only a few elements of this will be a little puzzling if you're not familiar with calc. For instance, this part shouldn't be too bad. Here's an algebraic data type defining syntax trees of expressions in our language. These are side effect free expressions, constants, variables, and two kinds of binary operators. And then here's a recursive function definition that, given a finite map giving values to the free variables and given an expression, computes the number the expression evaluates to. Then we have an algebraic data type of command syntax. This is where we have side effects. We're going to be able to read and write addresses in some mutable heap. So we have variable assignments, reading the value from a memory location into a variable, writing a value into a memory location, then sequencing and conditional. Then we can define our recursive interpreter for commands, which is basically threading through the values of our variables and our memory locations. That is a valuation and a heap, which are also the results of interpreting a command. I won't dwell on the details of how that all goes. I think most ICFP goers are used to writing recursive code like this that operates over syntax trees. And then finally, we can write a simple example program. I'm sequencing, reading from address 42 into variable x, and then writing back to that address the result of incrementing x by 1. I could also use an if in an example program here because I put if in my language. But if I wanted to use a loop or recursion or pattern matching or concurrency, I would have to add any of those into my list of command forms. Concurrency is kind of hard, but the others we're actually going to avoid needing to add explicitly with the technique that I'm suggesting. Also, we're going to avoid the explicit variable management. Here we see I'm threading evaluation, telling what the variables are holding through all of this. The technique that I'm going to show you gets around both that and the need to enumerate standard control flow constructs that should be inherited by the language that you're studying, so you can focus your attention on, say, the interesting side effects that are the primary part that you want to prove theorems about. So let's actually do some surgery on this example. We will get rid of the whole notion of expressions. We'll actually inherit expressions from the meta language calc. Similarly, I will simplify our command language. This is actually going to look sort of like monadic programming. In Haskell, let's add a return construct that just takes a number as input and makes that the result of this command. We're actually going to change commands to generate results, not just cause side effects. And then I won't need this anymore. Let's take sequencing and turn it into a monad-style bind operator. Looks like this. Takes two commands as inputs. First one's just a command. The second one's a function from the number that's the result of the previous command to a new command. And now all of our commands can return values. So reading a memory address no longer needs an associated variable. It just needs an address, and writing will take an address and a value to write there. And then that's it. I'll just ask calc to type check this for me. Yep, we're good. Okay. So next thing, let's just rewrite our interpreter. I'll remove the variable evaluation because we've now pushed off variable tracking into the meta language calc. So I'll return a heap and a number when we interpret a command. The number is the result of the command. So for instance, when we return n, that gives us the original heap unchanged and n as the answer. Won't need assignment anymore. Won't need if anymore. I will want sequencing to remain under the guise of bind. It's going to look pretty similar, no more variable evaluation. And then I change it so that I evaluate the first command, then I take its answer, and then the number part of that gets passed to the function C2. Otherwise, it's the same structure as we had before. And then reading gets simpler. We read an address, we write an address and a value. So reading leaves the heap unchanged, and then just returns the result of looking up address A, and then writing just writes the value we gave to the address, and then let's say whatever, it returns 0 as its answer. All right. And before I rewrite my little example program, I'll just add a notation here. When I write this with a little left arrow and a semicolon, sort of like a do notation in Haskell, what that really means is bind C1 and then a little lambda abstraction around C2. And so I can rewrite this one much more naturally, I would argue, like so, and then like so, back to address 42, x plus 1. Okay, so this may remind some of you of a variable binding technique called higher order abstract syntax, well known in semantics and plain old programming, because we are representing binders with functions of the host language. A key objective of higher order abstract syntax is to avoid what are called exotic terms that let you basically introduce new programming patterns that aren't explicitly defined in your syntax trees. But when you want to get students going quickly, writing interesting programs and verifying them, it's a great advantage to be able to stealthily introduce new programming features without having to enumerate them in your syntax trees. So let me show you that in action here. I'm going to write a little function that searches the first n addresses of memory for a 0. So n is the number, that upper bound on the part of memory to look at. And so this is a recursive function returning a command. What do? Look at n, and if it's 0, we're done. We return 0 because we didn't find a 0. Sorry for the multiple senses of 0 here. Otherwise, there's some address left to search. I'm just going to read from address n prime, and then if what I read is 0, then I'll return 1. We found a 0. Otherwise, continue the search, decrementing the function argument by 1. And there we have it. So this is cool because I've written a program that effectively uses if, recursion, and pattern matching. I didn't have to define a single one of these in my language of commands. They were all inherited from the meta language. And in fact, this kind of approach generalizes to let us mix arbitrary meta language control flow constructs with arbitrary object language side effects, not just mutable state. We can even do all kinds of concurrency. And this may seem familiar to you from, say, monadic I/O and Haskell for adding side effects. Yep, it's a very similar idea, but crucially, it supports induction on program syntax, which we need for all sorts of meta theorems. So we can add operational semantics, prove type safety, we can do Hoare logic, abstract interpretation, model checking. All that works great in this approach, and it's much more lightweight than more standard styles that you see in other sources. So that's pretty much all I have to tell you. The materials for this course, I think, are ready for other people to adopt today. You'll find the URL at the bottom of this slide, and please drop me a line if you're interested. Thank you.
Hi everyone, my name is Derek Dreyer, and it's my pleasure to tell you about GhostCell, separating permissions from data in the Rust programming language. This is joint work with my students Josh Yanofsky, Hai Dong, and Ralph Jung at the Max Planck Institute for Software Systems in Germany. Let me get straight to the problem. The problem that we're tackling in this paper is that although Rust makes it easy to implement tree-like data structures, that is, data structures that are acyclic and where each node has at most one other node pointing to it, Rust makes it hard to implement graph-like data structures, that is, data structures that may contain cycles or where some nodes may have multiple pointers pointing to them. And in the rest of this talk, I'm going to explain to you why this is the case and what we can do about it. But let me start with a little background on Rust. Rust is a new programming language developed actively over the past decade, whose high-level sales pitch is basically that it supports safe systems programming. On the one hand, like C and C++, Rust provides low-level control over memory allocation and data layout, which is critical for applications like web browsers or operating systems. But on the other hand, Rust is designed to avoid the pitfalls of C and C++ by guaranteeing type safety, memory safety, and data race freedom. The core idea that Rust uses to ensure safety is that the root of all evil in systems programming is sharing or aliasing of mutable state. And so Rust's type system enforces a discipline known as aliasing XOR mutability, or AXM, which says that there can either be multiple aliases or references to a value, or it can be mutable, but it can't be both at the same time. To enforce this discipline, Rust relies on the concept of ownership. By default, values are fully owned, which means that if you can refer to some value x of type t in your scope, then you know that there are no other aliases to it in the rest of the program, so you can read, write, or even deallocate x without worrying that you're creating dangling references or data races or things like that. However, if you want to create aliases to a value, for example to pass it by reference, then that's called borrowing, and you have two ways of doing it. You can either create a shared reference or a mutable reference, depending on whether you want to allow multiple aliasing or mutation. If you want multiple aliasing, then you create a shared reference of type &t, which you can copy freely, but you cannot use to mutate the value. If you want mutation, then you create a mutable reference of type &mut_t, which you cannot freely copy. It's a unique alias, but you can use it to mutate the value. So first let's start with the good news. Rust's AXM discipline works great for data structures with a clear tree-like structure, and the reason is simply that trees do not have any internal sharing. In other words, each child of a node owns a completely disjoint subtree from the other children, and so that greatly simplifies ownership reasoning. To make this more concrete, here's how you might define a tree type in Rust. The node type has a data field of type t, and left and right children, which are optional pointers to nodes. Now, the pointers to nodes are represented by this node ref type, which is just defined to be a box of node t, box here being the Rust type of an owned pointer, a pointer that owns the thing it points to. And the key thing here is that because left and right are separate fields of this owned pointer type, that means implicitly that they do not alias. In other words, they point to disjoint subtrees. That means that if we have a mutable reference to the root of the tree, we can safely use that to obtain a mutable reference to any node in the tree. This tree data structure also works great with shared references. If you have a shared reference to the root of the tree, you can use that to obtain shared references to all the nodes in the tree. And you can duplicate those shared references freely so that multiple threads can read from the tree concurrently. Okay, so that's the good news. The bad news is that the AXM discipline does not work well for implementing data structures that do have internal sharing. In other words, where a node of the data structure may have multiple other nodes pointing to it, which is the case in general in graphs as well as in doubly linked lists, like the one shown here. You see here that each of the nodes has two references to it, one from the previous and one from the next node. And so as a result, the only way to implement this in Rust, naively at least, would be to represent the links between nodes with shared references, since those are the kind that permit multiple references to the same node. The trouble is that if you were to naively make all the previous and next links in the doubly linked list into shared references, it would render the linked list type useless. Specifically, you can see here on the left the tree type we showed before, and on the right, the new doubly linked list type. The only difference between these types is that we've changed the type of node links from the box type we had before to a shared reference type. But in doing so, the links between nodes have all become immutable. You cannot mutate through these references. And that's a disaster. If you can't mutate through these links, then you can't even construct a linked list in the first place, let alone mutate it. So this all begs the question, in Rust, is there any way to implement data structures with internal sharing at all? It turns out the answer is yes. There are two approaches that one can use, and both of them are effectively ways of working around the restrictions of the AXM discipline, but neither is really satisfactory. The first approach is to use Unsafe Code. Rust provides a variety of unsafe features as a kind of escape hatch for programmers to use when the AXM discipline gets too restrictive. For example, You can use raw pointers, where the aliasing is not tracked by the type system. And this is, for example, what Rust's linked list library uses in its implementation of doubly linked lists. But once you use raw pointers, all bets are off. The language offers no safety guarantees for code that uses this feature, so obviously we want to avoid having to use unsafe features like raw pointers, if at all possible. The second approach is to instead use one of the various so-called cell types that Rust provides. Cell types allow you to wrap a value of type T in such a way that you can safely mutate the value even if you only have a shared reference to the cell, a kind of functionality that in the Rust world is called interior mutability. Now, on the one hand, interior mutability sounds like exactly what we want in the case of a graph or a doubly linked list. The nodes in the list are shared, but yet we still want to be able to mutate them. On the other hand, of course, there's no free lunch. Obviously, mutating shared state is not safe in general. And so in order to be safe, these cell types come with a variety of trade-offs. Some have pretty restricted APIs, some are not thread safe, some incur dynamic checks upon each access. In particular, if you want to be thread safe and allow concurrent reads of the underlying value of type T, basically your only option is RW lock of T, which synchronizes access to the value of type T with a reader-writer lock. So using RW lock, we can take our doubly linked list type definition that we saw before. Remember, here we were naively defining node ref using a shared reference type reference to a node, which meant we couldn't mutate it at all. And we can instead replace that with a shared reference to an RW lock of a node. With the RW lock wrapper in place, we can then safely mutate through a node reference. But unfortunately, doing this comes at a huge cost. Specifically, we are attaching a separate reader-writer lock to each node of the list. Now, that could be appropriate if you want to allow multiple threads to mutate the list at the same time, but if you just want to allow the list to be accessed according to the AXM discipline, in other words, either allow a single thread to mutate the list or multiple threads to read the list concurrently, then per-node locking is massive overkill, very expensive. So to sum up, yes, you can implement data structures with internal sharing in Rust today, but you either have to give up on safety or give up on performance. Is that a fundamental trade-off, or can we do better? And the answer is, of course, yes, we can do better. In this paper, we propose a new solution to the problem of implementing data structures with internal sharing in Rust, which we call Ghost Cell. Ghost Cell is a new cell type, which, like the existing cell types, provides support for interior mutability, for mutating safely through a shared reference. But unlike the existing cell types, Ghost Cell overcomes the trade-off between safety and performance. First of all, it's efficient. Ghost Cell is a zero-cost abstraction, meaning that it does not incur any dynamic cost in terms of time or space. Second of all, it's safe. We've done a formal proof that Ghost Cell is a safe extension to the Rust language, and we've mechanized that proof within the Rust Belt framework, which is implemented in Coq. And last but not least, it's flexible, meaning that unlike some existing cell types, Ghost Cell is thread safe and does not place any restrictions on the type of data being shared. The design of Ghost Cell is rooted in the observation that Rust's existing approaches to interior mutability incur unnecessary overhead for data structures with internal sharing because they tie permissions to data. That is, they enforce the AXM discipline at the granularity of individual aliased values, which is too fine. We already saw that it forced us into wrapping each node in the doubly linked list with an RW lock. The key idea of Ghost Cell is to instead allow you to separate permissions from data. Ghost Cell lets you associate a single permission with a whole collection of data, like the collection of nodes in a linked list. Whoever has read or write permission to the whole collection can then read or write any node in the collection without any additional synchronization or dynamic checks. Concretely, Ghost Cell realizes this idea using an old trick from the functional programming community called branded types. You may be familiar with branded types from the ST monad in Haskell. We call them branded types because they are types parameterized by a brand, which is a kind of static representative of a dynamic data structure. Specifically, we introduced two new types, Ghost Cell and Ghost Token. Ghost Cell IDT describes a cell type for wrapping data of type T that belongs to some larger data structure, such as a doubly linked list, with brand ID. And Ghost Token ID describes the permission to access the contents of any ghost cells that are branded with that same brand ID. To get a feel for how this works, let's look at how to use Ghost Cell to implement doubly linked lists. Here you see the type definition we showed before with RW lock, and the first thing we're going to do is replace RW lock with Ghost Cell, since that's our new cell type. We then also have to parameterize the node data type over the brand ID, which will represent the entire doubly linked list that the node belongs to, and we just thread that parameter throughout the type definition. Lastly, note that Ghost Cell is really a zero-cost abstraction, so the runtime representation of this node ref type is the same as if we had defined it using a naked shared reference. Okay, so now that we've defined our node type using GhostCell, let's see first how we can use it to construct a doubly linked list within a single thread T1. The first step is to create a new ghost token with a fresh brand ID. This gives us unique, mutable ownership of the ghost token that we're going to use to control access to the linked list. So now let's start adding nodes to the list. We can first create a new node storing the data, say 41. And then if we want to put this node under the control of the ghost token, we can use the fromMut method from the GhostCell API to wrap this node with a GhostCell with brand ID, the same brand as the ghost token. And that means we'll be able to mutate this node given only a shared reference to the GhostCell, so long as we control the ghost token. We can do the same thing with the rest of the nodes in the list. We can allocate them and then wrap them with GhostCells at the brand ID. And now comes the interesting part. We want to link these nodes together, which involves mutating their next and previous fields. To do this, we're going to use the borrowMut method from the GhostCell API to trade in our unique reference to the ghost token in exchange for a unique mutable reference to any one of the nodes in the list. In this case, we choose the first node. And that allows us to then update its next field to point to the second node. We can then regain ownership of the ghost token by giving up control over that first node. And we can then do the same thing for each of the other nodes, trading ownership of the ghost token for temporary ownership of each of the nodes in order to link them all together to form the doubly linked list. Finally, we can also use our ghost token to enable concurrent reads of the list from multiple threads. The key point here is that just as you can use a mutable reference to the ghost token to obtain a mutable reference to any node in the data structure, you can also use a shared reference to the ghost token to obtain a shared reference to any node in the data structure. In particular, we can first take our mutable reference to the ghost token and reborrow it as a shared reference, which we then freely copy and share between threads T1 and T2. And these threads can then use the borrow method from the GhostCell API, together with these shared references to the ghost token, to obtain shared references to all the nodes in the list. And using those shared references, the two threads can then perform unsynchronized reads of all the nodes in the list concurrently. Okay, so now you've seen how you can use a single ghost token to control access to all the nodes in a list. But that begs the question, how do you control access to the ghost token itself? And the answer is, you can do it however you want. Rust provides a variety of mechanisms for controlling ownership of objects. For example, you can use fork-join parallelism to temporarily share ownership of the ghost token between multiple threads before getting back unique ownership at the end. You can use channels and message passing to transfer unique ownership of the ghost token directly from one thread to another. You can use locks, like the reader-writer lock we saw earlier in the talk, to synchronize access to the ghost token between multiple threads. But notice here that we're just using a single lock to protect the entire linked list, not one per node. The key takeaways here are that by separating the permission, in other words the ghost token, from the data, in other words the ghost cells that it's controlling, we allow you to use a single permission to control a whole data structure, even one with internal sharing, and you can manage ownership of that single permission however you want, using the existing means of ownership control that Rust provides. If you found this talk interesting, there's a lot more in the paper. First, we give details of the GhostCell API and examples of how to program with it. In order to encode branded types, the API relies crucially on the old trick of using rank 2 polymorphism to generate fresh brands. This is inspired by Haskell's runST mechanism, except that in Rust, we have to represent brands using lifetimes rather than types, because Rust only supports rank 2 polymorphism over lifetime parameters, not type parameters. We also give an empirical evaluation to show that GhostCell outperforms other linked list and graph implementations on several micro-benchmarks, and we give a detailed description of our soundness proof for GhostCell. This is done as an extension to the Rust Belt soundness proof for Rust, and it was a non-trivial extension in that it required us to change how Rust Belt models lifetime inclusion. Thank you all for listening, and I'm looking forward to your questions.
Hello and welcome. Today I'm going to talk to you about Català, a programming language for the law. This is joint work with Nicolas Chatin and Jordan Brudzenko. Let's start with an example that will illustrate the subject of our study. This is an excerpt from the US tax code, and more especially the section 121, which defines how much you can exclude from your gross income whenever you have made a gain from the sale of a property which you have owned or used in the recent past. There is also a paragraph which limits how much you can exclude. This example showcases what we're going to try and formalize, which are decision procedures that are specified by legislative text, and those procedures should be completely without any human intervention. We're not going to try and formalize what the judge would do. There shall be no ambiguity, which is a hard criteria since law is all about ambiguities, but we'll find a way. And the decision procedure should talk about quantitative data, which we can observe and make computations on. So let's take that example and try to turn it into a pseudocode and effectively formalize it. We're defining the income exclusion variable, which is defined as 0 in the base case, and then a gain from a sale or exchange of a property if a certain condition is met. Note the inversion of the base case and exception paradigm with an if then else here. This condition is actually quite complex and involves computations on periods of ownership and periods of usage, which have to be truncated 5 years ago before the date of the sale, and then we're going to aggregate them and compare them to a 2 years ratio. Note that as of now this translation is somewhat ambiguous, since we have chosen to do 2 separate comparisons for the periods of ownership and usage, and the two-year period on which we do the comparison is itself ambiguous, since a year can either be 365 days or 366, so we would actually need to disambiguate those things. And to know which of those things we had to take, we just have to call a lawyer, because this is not inside the text of the law. And of course, to model the exclusion, we have to define another variable, which is a capped version of the previous quantity by the limit, which is $250,000. As you have seen on the previous example, turning law into code is a difficult task, and it is a task that is done regularly by employees of large organizations in the public and private sectors all across the world. For instance, in France, in the public sectors, all of those algorithms are in production and they compute various taxes and social benefits. They are coded up in diverse languages, which can be very old, like COBOL, and their size is very respectable. We're talking about dozens or hundreds of or even millions of lines of code. And the US situation is no better. The IRS income tax is implemented in an assembler of a computer from the 60s. Because of these respectable sizes and the difficulty of turning law into code, legal expert systems, which is the proper name of those software systems, can have costly and impactful industrial failures. Let's take 2 examples. The first one is the French Army payroll software Louvois, which has a very complicated rules for computing soldiers' bonuses. Launched in the early 2010, it has known a series of catastrophic failures, leaving soldiers without any resources for extended periods of time, and has cost hundreds of millions of euros of surplus cost for the project. Closer to the US, and more recently, the stimulus check distributed by the US government, which may seem as like an easy task since everybody should get one. Actually, there are subtle criteria to distinguish who is eligible or not to the check, and several dozens of thousands cases has been incorrectly declared as ineligible because of various commercial tax software error or subtle error into considering, for instance, the status of military spouses. Because of those failures that are documented, and we believe that there are more undocumented failures of this style, we have studies what is the current state of the art for code validation of legal expert system. And we have found that although test cases is the more common form of validation, there's a pattern of undertesting of those systems. And this pattern has structural reasons. First, the combinatorial explosion of cases can lead to needing several thousands of test cases. For instance, when you want to describe a fiscal household, there are many situations. For instance, you have one children, two children, your income should be in 1 or 5 tax brackets, and this leads to an explosion of test cases needed. The complete review and update of these test cases is necessary after each legislative change, a situation which can occur as frequently as each yearly. So this puts a heavy stress on maintaining that code base, and the maintenance has to be done by lawyers because lawyers have to compute manually the expected result of each computation. In short, this current state of the art is not satisfactory, and we believe there's a need of a better communication medium for lawyers and programmers. And this is the sense of this work, whose highlight is to mix code and law in a single document and make it easy for lawyers and programmers to work on this document, and also validate that the formal specification of the algorithm is faithful to the legal interpretation of the legislative text that's define it. To do that, we created a domain-specific language for the law and have 3 major contributions that are presented in the paper. First, we present the general syntax of this domain-specific language that has to be usable and reviewable by lawyers to ensure the correctness of the code. Second, we present a formalized semantics for this language, which is actually fits for the structure, the logical structure of legal documents and legal reasoning. And third, we certify partially the compiler of our language. This language is called Catala, and I'm going to present you an example of what it looks like on a section of the US tax code. As you can see, the idea is really to mix code and law in a very tight fashion. So we're going to take like one sentence of the text of the law and then embed a snippet of Catala code that directly translates this sentence. Here, this example is split into 2 parts. So there's paragraph A, which defines a qualified employee discount in a certain case, and then there's paragraph B that defines it in another case. And you can see that the Catala code adapts seamlessly within the structure of the legislative text, because here we would be defining the same variable twice, and Catala supports that under a condition, and each paragraph has its own condition which can distinguish what is being applied. This structure, and which is also the structure of the language, has been emphasized by Sarah Lowski, a tax lawyer in 2017 and 2018, and she shows in her work that legal reasoning and the structure of legal documents follows a non-monotonic logical pattern. Here you have another section of the US tax code, and we're going to highlight the logical structure of it. So this green part sets the condition from the base case of this $500,000 limitation. And then the lighter green part is the consequence of that base case. But then paragraph B showcases an exception to the base case, which has a different consequence. And this example showcases the dichotomy between base case and exception that is prevalent throughout the structure of the text of the law. And this is a structure that we integrated as a first-class concept in the Catala domain-specific language. So here is another example of a Catala program. The surface syntax is very verbose and has been co-designed by lawyers who have actually picked the keywords so that they can actually read and understand them. But for the formalization, we're going to go for a core of that language, which is attainable after several desugaring steps. And this formalized core, we have given it the name of default calculus. since it's just a lambda calculus with a default term whose form is shown on this slide with the label D. Let's look at how this default term executes. So on the left side of the default terms you have the exceptions, and on the right side you have the base case. So first case of evaluation of these default terms, there are no exceptions, or they all evaluate to this empty error term, and the condition for the base case evaluates to false. Then the whole term evaluates to empty error, which means that this thing doesn't apply. If the condition for the base case is true, then we're going to return the value of the consequence associated to it. Now, what if there is one exception that triggers and all of the others don't trigger? Then we're just going to return the value associated to that exception. And this actually encodes the priority of the exception over the base case. But if the legal text is badly drafted, then several exceptions can trigger at the same time, and in this case we return an error because the priority between the exceptions has to be disambiguated through legal reasoning in the source code. The schema we intend for deploying Kata in production is that of a compiled language rather than interpreted language, with a single source of truth that can be compiled to basically any programming language, which C for batch computation, JS for online simulators, or MATLAB for economic models. For that, we need to use advanced techniques of compilation, which basically amount to compiling our default calculus to lambda calculus. And here's the critical compilation steps. We take this default term, and then we're going to process the exceptions one by one, which we have to func because otherwise they're going to get evaluated early. And then we're going to see whether an exception triggers or not, and if not, then we'll just evaluate the base case with the condition. This process exception helper is a simple fold left with an accumulator that is an option type. You can refer to the paper for more details. This compilation of default terms has been certified within the F-star theorem prover with a simulation theorem whose picture you can see on the slide. It is a somewhat advanced version of a simulation theorem because the order of execution may differ between the source and the target language, but overall the evaluation results is the same. In conclusion, turning law into code is difficult. Programmers and lawyers need better tooling to do that. And to answer that problem, we developed the Kata language with 3 major contributions. It is a domain-specific language that is meant to be usable and reviewable by lawyers to ensure that the code is correct. It has formalized semantics that are adapted to legal reasoning, and that is based on the fabulous work of Sarah Lowski. And third, we partially certified the compiler and thus raised the level of assurance that we have on our compilation toolchain, making it a robust toolchain that is amenable for production deployment. As future work, we want to extend the compilation of Kata to other languages. Right now we have OCaml in Python and JS, and we want to connect Kata to proof backends in order to enable the proof of several properties about that text of the law. Thank you very much.
Hello, I'm Nicholas Crowther, and welcome to our presentation on persistent software transactional memory in Haskell. In recent years, persistent memories, which are also called non-volatile main memories, have been gaining traction. They fill the gap between storage and DRAM with their unique characteristics. They are byte addressable, offer latencies comparable to volatile memory, and are a viable candidate for mass long-term storage due to their large capacities and persistent properties. From the application's perspective, persistent memory can be used in the most performant way using its direct access mode, where it's mapped directly into the application's address space. However, this has many new challenges for the application developer that were previously externalized to a file system or a database. The right-hand side shows an example of the modification of a FIFO queue through the API of Intel Persistent Memory Development Kit, also called PMDK, which tries to reduce the complexity of programming for persistent memory. However, there are still many new obstacles that need to be handled manually. First, the persistent memory region needs to be explicitly mapped into the application's address space. The access to all data structures needs to be ensured at all times, and atomicity needs to be expressed correctly. Here, PMDK uses the well-established persistent memory transaction semantics. However, in this case, the application developer still needs to ensure that the transaction cannot be breached, as mutating global state outside of the transaction is still possible. Additionally, data needs to be explicitly allocated and referential integrity needs to be ensured at all times. This includes the correct and explicit management of lifetimes of reference structures, as well as that no transient structures are referenced that would be lost across the application runs. When using any kind of multi-threading, this example would get even more complex for PMDK, as the application developer would need to handle this additionally, as the library does not manage any of it in the background. We analyzed many existing solutions written in C, C++, Java, Go, and so on. While they offer some kind of alleviation through high abstractions such as concurrency guarantees and automatic memory management, they still allow for some kind of inconsistent usage of persistent memory. For example, they cannot transparently avoid assignment of volatile structures. We argue that for languages with such a low memory abstraction that offer arbitrary byte or field level access, there's always going to be some kind of trade-off, as the imperative language model itself is the problem. It is not restrictive enough, as arbitrary modifications are allowed which result in large overheads when traced by the runtime system. Thus, PM cannot be safely integrated into these languages as an afterthought. So we asked the question, can we design a system that ticks all boxes, that handles all the challenges discussed previously in the background without the application developer needing to worry about it? And we found that with their limited mutability, purely functional languages are exactly the right paradigm, as they offer the right constraints to build very transparent abstractions when working with PM. We can design specific solutions for the limited set of mutating operations that are available in the language. As a proof of concept, we modified the Glasgow Haskell compiler that didn't know anything about persistent memory before. We integrated our solution into the runtime system of the language to support persistent memory as a first principle. For this, we designed a hybrid heap that is persistent across runs and directly extends the volatile heap by mapping it into the application's address space. We use a fixed mapping that's handled transparently by the runtime system to ensure the integrity of references in PM across runs. And we only store native closure objects in persistent memory to allow direct access at any point without serialization or deserialization. As we are fully integrated into the memory management of the language, we provide garbage collection of PM through a reachability-based mark and sweep collector that is based on the recently introduced Alligator garbage collector found in GHC 8.10. Also, we integrated a PM-tailored allocator design that uses minimal logging and is specifically designed for Haskell closures. To interact with persistent memory objects, we chose to use the well-established persistent memory transaction semantics. For this, we extended Haskell's implementation of software transactional memory, which is very well integrated and used by many application developers to ensure the concurrency-safe modification of specific mutable variables called TVARs. we introduce PTVARs as a direct persistent counterpart to those volatile TVARs. In our system, which we call PSTM, PTVARs can be created and modified with the functions new PTVAR, write PTVAR, and read PTVAR. For those of you that are familiar with the original STM interface, they strongly resemble the operations offered for TVARs. Additionally, we use a persistent programming concept called the persistent root that allows you to gain access to the persistent memory structures across runs. We provide the root as a unique PTVAR variable that can be obtained through the getRoot function. Using the passed argument, the value of the root is initialized on the first call to the function. All subsequent calls to the function return the current value and ignore the passed argument. As we are using the STM monad, we still allow TVARs and PTVARs to be modified jointly, so that volatile and persistent data can be modified in one single and power-fail-safe atomic transaction. To get a better feeling for our system, we'll show you a couple of examples now. When you want to access the persistent structures, you would call getRoot. In this example, it returns a list of PTVAR ints. The type of the persistent structure is determined by the initially passed value. We allow arbitrary PTVAR values so that you can have very complex structures that are stored without serialization in persistent memory. Also, what you can see here in this example is a direct reference X to a PTVAR that is not reachable from the unique root. This is fully supported, and the PTVAR functions as a volatile heap extension that is collected across runs automatically, as it's not available from the root. And this structure is only referenced through the volatile heap, which doesn't exist in the next run anymore. In fact, a memory structure is alive as long as it's referenced from either the volatile heap or has a transitive connection to the root PTVAR. Transient PTVARs can be used in scenarios where PM needs to be used as a volatile heap extension, as PM has much larger capacities than DRAMs. In this example, you can see how PTVARs can be jointly modified. Currently, there is X and Y in persistent memory, which we modify through the transaction, which you can see on the left. We first read them and then we add 5 to each one of them. So then only when STM ensures that the variables can be committed without any concurrency issues, there do we copy the data over to persistent memory. Then we use minimal logging to perform atomic pointer updates to ensure power-fail-safe execution. We do not need to log anything else, as our automatic memory management will take care of collecting any leftover data in the next run. Finally, Z is returned as a direct reference into the persistent memory heap, which can be used as any other Haskell expression. As our system is fully integrated into the language's runtime system, we can also support the lazy execution model of Haskell in order to offer an idiomatic language abstraction. So developers can store arbitrary functions and unevaluated expressions in PM. In this example here, we can see that X points to the expression y plus 5 with the environment y equals 1 in PM. In case that X is evaluated, any intermediate results will be created in the volatile heap first. While this is shown here with the integer addition, more complex intermediate results can contain unevaluated sub-expressions themselves. These then would be computed in volatile DRAM as needed, and only the final result would then be copied over to PM. Finally, the result pointer is updated consistently by using atomic pointer updates. Being fully compatible with the lazy execution model allows us to use many existing libraries that have never heard of persistent memory before. Here in this example, we use memoization libraries to create a memoized version of the Fibonacci function. By persisting and retrieving the memoized function, we obtain the persistent memoized function that internally tracks all previously computed Fibonacci numbers in PM. In this case here, the fixed point memoization not only stores the final result of a function application, but also all required sub-results. And this happens all transparently. In our benchmarks, we saw that for the memoizing of the first 150,000 Fibonacci numbers, we have an overhead of 4 to 5x when storing it persistently on Intel's obtained DC persistent memory, versus the volatile counterpart. However, now you can amortize this overhead across multiple runs and not just the current run. Finally, let us look at a comparison of PSDM with other persistent transaction libraries out there. We here show the results of red-black tree and hash table benchmarks. However, we have more in our paper. We analyzed the libraries OneFile, Romulus, PMDK, Mnemosiny, and compared it with our system. There is 3 possible operations that we perform on the data structures, either lookup or insert or delete with equal probability. The x-axis of the figures show the lookup rate, which is the percentage of transactions that only perform lookups, thus only do reads on the data structure. The y-axis is the transactions performed per second. So let's first look at the other libraries independent from our solution. We observed that for the analyzed data structures, the top solution is not consistent. For RB tree, the rebalancing introduced by updates of the structures can lead to updates of many variables that introduce many conflicts during transactions. Here, Mnemosiny shows similar performance to our solution as it relies on a SDM-like mechanism for concurrency control, while libraries such as OneFile and Romulus have high performance impacts as they do not allow for concurrent execution of write transactions. Hashtable, on the other hand, shows a different behavior. As it's a flat data structure and only few variables are being modified during insert or delete, the write transactions are sufficiently small and thus create much less blocking, thus leading to a higher performance of Romulus and OneFile. Mnemosiny's transactions are more heavyweight due to transaction logging overheads. However, we saw that PSDM shows very competitive performance to all other libraries. Note that we report 2 different configurations of PSDM, a blocking and an unlimited version. In the blocking configuration, we enforce a small size-limited heap to allow for fair comparison with the libraries that also reclaim obsolete objects in a timely fashion. The unlimited configuration is meant to serve as an upper bound for more optimized garbage collection schemes, as our garbage collector is not yet optimized for blocking collection phases where it does not benefit from possible multi-threading. In both configurations, PSDM heavily benefits from low logging overheads and SDM's excellent optimistic concurrency control, which makes it a viable and performant alternative to existing libraries that provide less abstraction. In conclusion, we can say that persistent memory is a very interesting new technology that can be used to access persistent data without any kind of serialization or deserialization. We showed you PSDM, a simple API extension that allows even novices to write persistent memory programs, as it hides pretty much all the details of the technology while preserving its high-performance access advantages. We think that the language level constraints such as limited mutability here make building concise and comprehensible abstractions possible. The runtime integration of PM resulted in a system that allows idiomatic Haskell to be used to interact with the new technology. As our design is compatible with lazy evaluation, adaptation of legacy code is trivial, which is in stark contrast to other approaches that can require large rewrites of code bases when introducing persistent memory. Thank you for your attention. Please feel free to ask any questions to us via email or in the discussion section of the conference.